Hi everyone, thanks for joining today's session. We are excited to share how we have built a system capable of processing 1 million identity graph per second using Spark structured streaming. Now, 1 million may sound abstract, but if you really think about it, it's like resolving the entire population of San Francisco per second. The challenge that we set out to ourselves was this: how do we continuously scale identity resolution, keeping the identity graph fresh in real time, and also being privacy compliant at all the steps? But before we dive in, let me quickly introduce ourselves. I'm Akanksha. I'm joined with my colleague Janmay. We are both engineers at Adobe, working as part of identity graph team. Our team is responsible for building and scaling identity services within Adobe Experience Platform. Our focus has primarily been on designing and developing high-throughput, large-scale data pipelines that are, most of our time is spent on technologies like Spark, Delta Lake, and Flink to make this happen. Moving on, let's take a look at the agenda for today. So we'll start with an overview on what is Adobe Identity Graph. We'll talk about our journey from where we were 5 years back and how we went to 10x. We'll talk about some of the scaling and optimization techniques and do a deep dive on what the problem was and how we solved it. We'll also talk about some of the privacy compliance strategies that we follow along all the steps. And then we do have our custom deployment workflows that are built on top of Databricks workflows. We'll share how we are managing that. And we'll wrap up with lessons learned and key takeaways, followed by a quick question and answer session. Before we dive in, I just want to see a quick show of hands. How many of you know Adobe, mainly from Creative Cloud and PDF? Well, thought so. That's what we are most known for. And how many of you know Adobe's work in digital experiences? Great to see some hands there. Well, for others, you are in the right place. So, Adobe Experience Platform. We have RTCDP that helps brand that unify customer data. We have data coming in from various sources, like mobile apps, web SDKs, and CRM updates. We unify all this data and build something called as unified customer profiles. All of this data then get activated on various channels, like LinkedIn, Facebook, email campaigns, and so on. Now, at the heart of the system is identity graph. Identity graph has an ability to resolve billions of customer identifiers across various devices and channels. So let's talk about how we stitch this identity graph. We have identity signals coming in from various channels, like web events, mobile SDKs. We stitch them together in real time. This stitched graph then power personalized campaigns and cross-device activation and measurement. But scaling this graph, both in terms of volume and freshness, has unique challenges. And that's where our work on Spark and Delta Lake comes in, ensuring real time with strong guarantees. Now we have talked about what identity graph is. Let's talk about the scale at which we operate. So we ingest petabyte of data daily. 70 billion records flow through our system every single day. And we process these messages at a peak of 1 million per second. All of this then feeds into identity graph. And we have built this service from the ground up. Before I dive in about our architecture, let's maybe take a step back and do a rewind on how we started. So, when we started, we have a service which is doing data collection from various channels, and it's then feeding it all onto streaming topics. Then we have our streaming processing pipeline using Flink, which was a single-layered architecture. So the single pipeline will look into reading the messages, processing them, applying the stitching algorithms, and then writing them back to identity graph store. And all of this was deployed on Kubernetes clusters. So this worked pretty well. And then we started realizing the challenges as we started scaling up. So let's talk about some of the challenges that we faced. The number one was operational overhead. So these apps were actually deployed on self-managed Kubernetes clusters. And these clusters will have to do continuous upgrades, manage the operational challenges, and also do the maintenance task, which is quite challenging for a team of software developers. The second bigger problem was, it was a single pipeline where we had the processing, reading, writing to storage all as part of same pipeline. So what that meant was, if we have newer topics coming in where the partition size increases, we could not really scale up same block because then we'll have bottleneck on when we are writing it to the graph layer. And then the third problem was noisy neighbor. So all these streaming pipelines have data coming in from multiple tenants. And if one tenant brings in more data, it can cause bottlenecks on the system and cause resource contention. So now let's take about our current architecture. So the first component that we see here is we have data collection, same as before, writing everything to streaming topics. Now, comparing it with what we saw as our initial architecture, with what we see on the slide right now, we have a multi-layered architecture compared to a single layered. The first component here, which we can see, is the data processing step. So this step is the one which reads data from Kafka. It also takes care of normalizing, enriching, and converting it to canonical format. All the writes happen to Delta Lake in append mode. And we rely on Delta Lake ACID capabilities to maintain strong concurrency guarantees and checkpointing fault tolerance. The second component that you see is data ingestion, which reads data from Lake and writes it to identity graph store. And data ingestion layer is the one where we apply our proprietary stitching algorithms to have different kind of identity stitching rules applied. And all of this deployed on Databricks clusters. Okay. But the current, going from the initial architecture to final architecture had some various phases. So our first phase was Flink on Kubernetes, where we had self-managed K8s and operational overheads with single pipeline. Then we started experimenting with Spark structured streaming to see if it will fit in our scale and go at least meet what we were doing and can go beyond. When we did our experiments, they looked pretty good, and we were able to get the same scale and also do a lot of more optimizations on top of it. And now the problem in phase 2 was we had some tenants migrated to Spark streaming, while some tenants which were on Flink. This was again operationally challenging to maintain. So in third phase, we had a fully managed Databricks deployments, no more Kubernetes clusters to handle these pipelines, and Spark structured streaming for all tenants. But again, like any other system, to grow beyond as we are scaling up, getting in more customers onboarded, we had to apply a lot more optimization techniques and solve various different set of problems. We'll talk in detail about each of these problems, how we solved it, but some of them were like noisy neighbor, rate limiting, metadata resolution, Delta Lake optimizations, checkpointing. So here is a quick look on the optimization techniques. Number one is micro-batching, where we are tuning the micro-batch intervals to fit into our scale and throughput requirements. We have data deduplication. We'll talk about what data deduplication means in context of identity graph. Then we have asynchronous task execution, where we have parallel I/O, so we don't have blocking I/Os. Also noisy neighbor problem, how did we address that? And then making sure we have an efficient resource utilization at the cluster level, where there's no skew. And also we'll talk about metadata resolution using in-memory snapshot-based lookup. So starting off with micro-batching. So as we scaled up our system, one of the most inefficiencies we saw was redundant ID graph updates. So in our pipeline, identity graph signals usually arrive from high-frequency sources, as we talked about before, like web events, mobile, and CRM updates. And these events usually carry similar kind of IDs, which can cause a bottleneck. So what we were doing is, we were processing all the events as they were coming in, writing to our graph store without any intermediate filtering. So you can imagine, like when you go to a website, you may browse to different pages, you may refresh your screen, you may go to a different product viewer section, and all of them within few seconds. When we talk about ID graph, all we care about is the ID relationship. We don't really care about how many times we saw it, because at the end of the day, it's the same ID that we're matching to the other ID. So because of this repeated writes, we were actually hammering our graph store for the same identifier edge 100 of times per user hour. And this had real cost, all in terms of compute, storage, as well as processing. So let's talk about how we address this problem. So we addressed this problem at two levers. The first one was micro-batching, and the second one was deduplication. So in micro-batching, we adjusted the micro-batch interval of a Spark streaming app in a way where we were able to give a natural coalescence of repeated events. Right? And now let's talk about deduplication. Within each batch, we applied like some sort of deterministic deduplication layer on ID pairs. With this, now instead of doing hundreds of writes per hour, we will emit one single canonical relationship into the graph. And this helped stabilize the load on backend. What we noticed was there was an 80% drop in the duplicate data, and our downstream systems were able to maintain and sustain much more load, and we were able to scale up easily. So in your pipelines, if you're seeing more load at the sink layer, be it a key value store, graph store, or external APIs, always think about maybe there's a potential dedupling that we can apply so that it can help with not just processing, but also being cost efficient. Because sometimes it's not about scaling. We can go as crazy and scale up our infrastructure, but sometimes we also have to think about removing that should not be there at the first place. Okay, moving on. The second strategy, or the second problem that we noticed in our system was data skew. Especially when we were reading from topics which were not of uniform sizes. So some topics would carry significantly high volume compared to others, and the Spark partitions which are actually polling from these topics will be overwhelmed. My team actually ran into this issue when we were scaling INT ingestion pipeline. And I want you to walk through how we solve this problem. So imagine that same Kafka topics where we have two categories. The first category is where we have identity signals coming in from high-frequency web browsing events, like analytics, page views, product views, etc. And this will carry almost 80% of the data compared to the other topic, which was relatively lower volume frequency CRM updates. Now, the Spark partitions on the streaming app, which were reading from the high-volume topics, were actually overwhelmed. And the Spark partitions, which were reading from lower volume topics, were underutilized. So how did we address this problem? We actually used an explicit repartitioning step after reading from the topics. This helped balance the skew dynamically and also helped us achieve better parallelism at the executor level. What we observed was, now we have a much better cluster utilization. Almost all executors have similar CPU percentage. And also we were able to bring down the straggler task by over 40%. Now you may question, hey, repartitioning is expensive. It is, because it introduces a shuffle. But then if data skew is not addressed early in your pipeline, the skew will carry forward anyway. And the next stages of your pipeline will have to pay for it. So why not address it early, and you can scale out horizontally to match out as the more load is coming in. So if in your pipeline you are seeing skew, or you should always think about how you can repartition in the most optimized way. And then this will help you save at a later time in both time as well as cost. Okay. Now I'm going to pass the mic to my co-presenter Janmay to talk about in detail on other optimization techniques. Thank you.
Okay. Yeah, thank you, Akansha. So I think we talk about the repartitioning that definitely improve the resource utilization. However, we still face the latency issues because by the time we are processing everything in sequence. So there's a big performance gain that comes when we introduce a customer asynchronous execution model. So basically, essentially our Spark thread, it will just getting bogged down because they are waiting for the database write to be finished. So every time we need to update identities to write to our graph store with the foundation database, the main thread just wait and stop and waiting, and that causing the bottlenecks. So that's why we implement a asynchronous multi-threaded execution model, where that instead having the main thread to wait for the database waiting, we can have them to assign a word to a dedicated thread pool, right? Then when the main thread will continue to process new tasks and without waiting. And more important here is the sliding window part. This is where we use it to control how many concurrency I/O tasks will be in order not to the overwhelm of database. So with this approach, I think the improvement is substantial. Like we have twofold improvement in the ingestion latency. We have better serialization, and we have much more consistent throughput at scale. Okay. The next one is when our service expanded to support more tenants, we run into the classic problem that in the multi-tenant system, the noise enabled. So you can think that like one customer, they maybe have misconfigurations, right? They are sending a lot of duplicate events, or maybe a bot that is flooding the system, right? And single tenants could just use a large chunk of data that impacting everything else. Then these are just some examples that were impacting caused by the noise enables. So one might think that we just simply fix to drop the extra events, but that is not acceptable because we don't want to lose customers' data. So instead, we create an elegant red limpet solution. So in this solution, each tenant, you will have a certain quota for the high priority processing. As long as that within that certain quota, everything flows quickly. But if it exceeds the limit, we are not dropping data. We just move them into a slow path, and that slow path have a controlled rate, run that to a different data table here, so that you're not impacting everyone else. So with this approach, I think it's predictable. It's fair. That we also prevent single tenant from causing issue for everyone, and you can avoid the taking over the shared resources. I think during one of our campaign, we have single tenants at like 1 million event per hour, and we code it with 5 minutes because of this approach. And then we trigger the random meeting, and we protect like 700 plus tenants for the ingestion pipeline. Okay. I think another big challenge we face is dealing with the anomalous identities. So what is anomalous identities here? So they are identities that are usually interconnected. So possible reason caused by the data quality issues, right? Or maybe some misconfigurations is also possible causing this connection issue. So imagine that you have one email address that's linking to like thousands of users. Or maybe a device ID is like connected messy numbers profile, right? That's kind of issue we're talking about. So then this is causing two major issues here. One is because when we process these highly connected identities, that's going to introduce a lot of simultaneous transactions that hitting the same identity clusters that will bring the overhead to our database and cause the conflicts. Right? And second is we're slowing everything down because we can share the multi-tenant system. So to address this, we define an anomalous detection system to detect this or to spot this behavior early. So in this approach, we continuously monitor for identities that start building unusual large connections, and then we flag these identities before they can cause a problem. And our detection system will look at several metrics. We will look at the rate of new connections being formed, the total size identity clusters, and the frequency of the multiple operations. So when any identity crosses our threshold, it will get ultimately flagged and routed to a special handling. So instead of processing these anomalous identities through our standard high priority throughput pipeline, we will isolate those into a separate processing track for different algorithms that can play on. Okay, now let's talk about something interesting here. So I think one of the performance issues that kind of caused us surprise is the overhead of the resolving the metadata in a long-running Spark application. So you can imagine that in that high throughput events, as new events flows in, we constantly needed to look up their metadata. So we look at, for example, like the tenant configuration, the schema mapping, or how we processing the rules for events. So that means that every time when we encounter a new tenant's ID, our executor will make the HTTP calls to fetch the external metadata service. And each call, it will introduce like 10 to 50 milliseconds per minute, right? Latency. And even though we have a TTL-based cache in place, we need to make thousands of API calls to get this information back. And this bottleneck is very easy to get worse when the events volumes increase, and they can put real pressure to the external metadata service. So our solution here was to use the Netflix Halo. It's an open source library that we can use to cache all the metadata in memory. So at the high level, with Netflix Halo here, it takes a snapshot of your data set and will compile it into a compact binary format. So that in that way, it avoids object creation. Instead, that by using the primitive array under the hood, and you don't need to deserialize it into a Java object because they use the typeset access API to access the field in the memory directly. So it's optimized for use case exactly like this, that you want to look at something small, something infrequent updates to the metadata, then this something that mappings or schema reference or the config rules, this is the one you can leverage. So what does it mean that? So once loaded, every executors, they will have a local cache that has the GC efficient, and you require minimum coordinations with the external systems. So that means that we just need to load this once, and then we will have that data in local, then for executors. And after that, lighting will be lookup will just lighting fast. That will reduce from milliseconds to nanoseconds. And of course, also it will eliminate the startup, like warming process when the time the job started, because all you need to do is periodically update if there's any underlying data change. Okay, now let's talk about privacy compliance. I think most of you might leverage the one key change that manage a production data lake is a key part is how to manage the files clean up while maintaining the same compliance and the data integrity, right? So I think data lakes vacuum is and it provides very useful pool. Let's talk about that. It's versioning. So the version is powerful because it allows for time travel, it allows the rollbacks, and allows the async transaction, right? Then data also provide vacuum operation that can clean the data files, that can improve the storage and the performance. But there's a tricky part here is how you can't be too aggressive, because if you're calling the vacuum too frequently, it might delete data that's still referenced or used by the ongoing processes. So our solution here is we actually create a marker-based approach. So after each micro batch that in the Spark structure meeting, every micro batch finishes its job and the changes are committed, we'll write a markup file to show that this file is safe to clean up. And this is ensured, and when our vacuum process started, it will only delete file under two conditions. One is data is older than the retention limit, or it has a markup file. So in this way, it can ensure that we don't accidentally delete anything is important, and we can keep out the storage clean without risking any data loss. Okay, now let's talk about deployment, the updates to our mission critical streaming applications. Right, so all the streaming ingestion, they are 24/7. That process millions of events that we cannot afford any downtime. So the traditional methods that involve in stopping the service, restarting service, is just something not an option for us. So here we provide a custom deployment mechanism, the blue-green deployment. So in this deployment, how it works like, we'll launch a new cluster, So all this deployment is built on top of the Databricks workflow. So whenever one tries to do a deployment, we'll deploy a new version of a cluster with a new virtual application. Then we will make sure when everything's stable, all we need to do is just to switch our traffic to a new cluster and gracefully shut down old one. And if anything goes wrong, we can quickly switch back by flipping the configuration flags. So this strategy has enabled over 25 Databricks workflows, and our CI/CD pipeline has seamlessly support for AWS and Azure environments, and I think that also built on top of our self-managed Jenkins infrastructure. So basically, with this approach, we are easy to manage our service, which is stateful, like a web service that's stateless, as simple as that is. Okay, let's talk about, let me just summarize what I have accomplished with all the optimization techniques and overviews about what the talks about so far. So through all these changes, we successfully scale identity graph ingestion to process more than 1 million events per second. It's a true 10x improvement from where we started. And second, our micro-batch and deduplication strategies lead to an 80% reduction to the redundant writes. That's cutting both storage and the overhead of the processing. And we also tackle the Kafka partition skew and the task imbalance by introducing repartitioning that reduce the struggle task and maximize our cores utilization. The multi-threaded asynchronous execution model gave us 2x improvement to ingestion latency while maximizing the utilization of the CPUs. And our rare limiting resolution solved the noise-enabled problems while maintaining the fairness across the tenants. And our optimization for the metadata resolution using Netflix Halo also gave us to reduce the latency from the milliseconds to the nanoseconds. And also, we have the privacy, everything is built under the privacy compliant. We have the compliant cleanup ensure in place. And the blue-green deployment can make all this deployment seamlessly with routine as well. I think the key takeaway from our team and what from this slide is like, what we shared today is a month of dedication, right? We're scaling the pipelines, we fine-tune the performance, we make sure everything's reliable and under compliant. So ultimately, I think the scale is success is not just about doing more, it's more about doing faster, better, and safer. So any one of you if interested in any topic further, we can disconnect offline. But then we'll have a Q&A questions after this. Okay, 感謝 join us.